Starting out here with number 1, we're trying to look at this scatter diagram and see if it indicates a linear relationship or not. And you can see that these points don't lie mainly along a straight line pattern. It looks like there's two separate patterns going on here, where here we're pretty much flat, and then further out we go, it starts to dip down. So there's not just this straight line pattern being followed. So for this example, the data do not have a linear relationship. A similar thing here with number 2. Here the points do lie mainly along a straight line pattern. So we could see if we drew a straight line here, all the points are lying along that route. And so we would say there is a linear relationship here between the explanatory variable x and the response variable y. And since that line is going down, has a negative slope, we would say the two variables have a negative association. For number 3, we have a data set, and we're going to start by drawing the scatter diagram. So you can do that in StatCrunch, and you'll want to go to to graph, and then scatter plots. And you select the x variable and the y variable, and when you hit compute, it comes back with the scatter plot. Now, pay attention to the scale here of the x and y axis. Notice the x is starting at 6 and going to 9, and the y is going from 5 to 9. So it's going to look different than your answer choices over here that all go from 0, starting at 0, 0. But focus on the pattern here of how the points are arranged. And another thing is you can notice the extreme values and line that up. So our furthest to the right value is also the lowest value. And so if you look back here, the only scatter plot that matches that with the furthest to the right value also being the lowest is this one here, which is the correct answer. And the points also follow that same exact pattern that we saw on the graph in StatCrunch. Now next we want to compute the correlation coefficient, which is going to tell us how strong a relationship there is between the x and y variable. So we can go into StatCrunch and go to Stat, Regression, Simple Linear. We're looking for linear relationships. So select the x and y variable, and when you hit compute, you'll see one of the things that gives you back is the correlation coefficient, that value right there. So round to the correct number of decimals. And then the final part here is to determine whether there is evidence for a linear relationship between x and y based on that correlation coefficient. So first, just note whether it's positive or negative. In this example, it was negative. But what we want to do to determine whether there's a linear relationship is look at the absolute value of that. So you're going to always enter the absolute value because that's what we're looking at. And we're comparing it to this, this table here of critical values. And since there were 5 pieces of data in our data set, we would look at where n equals 5. And if our correlation coefficient, if the absolute value was bigger than 0.878, there would be evidence for a linear relationship. Now, our absolute value was less than 0.878, so there's not evidence for a linear relationship. For number 4, we're looking at a table of data here comparing the commute time for adults to their well-being score, how overall happy they are in life. And so we're first going to just try to determine which of these could be the explanatory variable and which is the response variable. Now, the explanatory variable is the one that is affecting the other variable. And so commute time would be the explanatory variable because, based on how long you have to drive every day to work, that can affect your overall well-being, your happiness in life. But it doesn't work the other way around. Your commute to work, that distance, that time is pretty much fixed based on your job and where you live. And just because your happiness in life changes, that's not going to change your how long it takes to get to work. So the commute time can be the explanatory variable, and it affects our response variable, our well-being score. And now I've opened up the data in StatCrunch, and I want to go to Graphs, Scatter Plot. And so our explanatory variable needs to be x, so that is our commute time, and the response here was our well-being score. And when I hit compute, we see the scatter diagram here. And again, note the x and y axis, the values, they don't start at 0, 0 down here. But look at that overall shape. It's definitely trending downwards. And we want to match that to the correct graph. So there's only two graphs that are showing a downward trend. And this graph is definitely the correct one. It's got that single point off by itself at the far right end. And here it looks like there's more of a cluster down at the end. Um, and that single point off by itself at the bottom is matching what our scatter plot looked like in StatCrunch. So now calculating the correlation coefficient, we would go to Stat, Regression, Simple Linear. Commute time is our explanatory variable, and our wellness score is our response variable y. Correlation coefficient comes right here. So we want to type that in for our answer, and we're going to look at the absolute value of that and compare the absolute value of that to the critical value for how many pairs of data we had. And there's 7 pairs here, so we want to look at the critical value. The number for 7 is 0.754. So our absolute value here is higher than 0.754. So there is evidence of a linear association, and it would be a negative linear association because our R is negative, and we can also see it from the scatter plot. The line this data seems to following is a negative sloping, downward sloping line. Number 5, looking at the relationship between a disease, Lyme disease, and the number of drowning deaths in a rural county. So we're going to make Lyme disease our explanatory variable and see if somehow that is having an effect on the number of people who drown. So Lyme disease should be on the x-axis, and our y variable response will be drowning. And we're going to start off by looking at finding the right scatter diagram. So we want to open this up in StatCrunch. And there's some extra data here, the month of the year. That's not actually necessary for what we want to do. We just want our scatter plot connecting the cases of Lyme disease with the drowning deaths. And then when we hit compute, we see our scatter plot. So we're going to look for this pattern in one of the answers, and you'll see it's right here. And then the next part is to find the linear correlation coefficient. So we do that with regression, simple linear, and hit compute. And it gives us the correlation coefficient. So we're going to compare that now, the absolute value of that, to our critical values table. So how many data sets did we have? We had 12, one for each month of the year. So we're going to use a critical value here for 12, which is 0.576. And since our correlation coefficient is larger than the critical value, that is evidence for a linear relationship. And since it's positive, it would be a positive linear relationship. If the correlation coefficient was less than our critical value, that would mean there is not enough evidence for a linear relationship. For number 6, we have a data set here of x and y's. And we're going to first start off by drawing a scatter diagram for those. So we'll want to open that up in StatCrunch. And if we go to graph, get our scatter plot here, when we hit compute, we see what it would look like. And so these points do appear to be mainly on a straight line that is sloping downward or negative. So just from looking at the scatter plot, it does appear that there could be a linear negative relationship between x and y. Now to calculate the least squares regression line, which is the line that best fits through all of these points, it's the line that's as close as it can get to all of the points at the same time. To calculate that by hand, you have to do a bunch of computations, but we're going to use StatCrunch to do those computations for us. So simple linear between our x and our y, it's going to come back and give us right here that least squares regression line that we want. Now notice how it's written, the part with x is actually second, and your y-intercept part is first. So it's kind of backwards of how you have to enter it here when you type in your answer, but that is the least squares regression line. And so the last part of the problem is just to combine those two parts, actually graph this line on the scatter plot. So it's going to look just like the scatter plot, but with a line going through it that is the best fit line. And so here is that same scatter plot, but with the line going through it that we computed right there. And back in StatCrunch, you'll notice it says 1 of 2 here. There is the option to actually see the scatter plot with the line drawn in just by clicking the arrow here at the bottom to go to screen 2 of 2. And so that's drawing that best fit line. If you hover over it, it actually puts the equation up there as well. But it's combining your scatter plot there of your x and y points with that least squares regression line drawn on there. For number 7, we're looking at the relationship between the weight of a car, that's our explanatory variable, and the car's gas mileage, that's our response variable. So we're going to open the data we have in StatCrunch, and we want to look at the simple linear regression here of how the weight can affect the gas mileage. And when we hit compute, we get our least squares regression line right here. And notice the number here at the end is the one that's multiplied by x, the weight, and then this part here would be the y-intercept. So make sure you write those in the correct order for your answer. In part B, we're going to interpret the slope and the y-intercept. We always interpret the slope. It is a measurement of how much the y variable will change when x changes by 1. So in this context, it's how much the gas mileage will change, that's our y variable, when x, the weight of the car, increases by 1. And so it looks like the gas mileage will change by going down, being negative this amount whenever a car's weight increases by 1 pound. The y-intercept is the value that y will be, in this case gas mileage, when x is equal to 0. And that doesn't make any sense in this context because x is the weight of a car, and it doesn't make sense to have a car with a weight of 0. So we should not interpret the y-intercept. For part C, we're told that we have a certain gas-powered car that weighs this amount and gets this many miles per gallon. And we want to know if this is above or below average. And we're going to look at the least squares regression line, which shows us what the average is for each different weight. So for a weight of, in this case, 3,600, you would plug 3,600 in for x. And I've done that over here using Excel as a calculator. Just plug 3,600 in for x, and the least squares regression line tells us that y, the gas mileage, should be this, which is right around 18. And this car that we were looking at only gets 17. So this particular car here is below average for cars that weigh 3,600. So for any gas-powered car we have, we can plug in its weight and get a calculation of what the average gas mileage should be. But part D is saying, can we do that for different type of cars? Can we do that for a hybrid gas and electric car? And the answer is no, because this is a completely different type of car. So this data we used here doesn't incorporate or have anything really to do with hybrid cars. So we should not use the least squared regression line that came from this data to make any sort of predictions about a different type of car.